Sklearn naive Bayes. Description naive Bayes is a probabilistic machine learning algorithm based on Bayes' theorem that is used for classification tasks. It assumes that the features are independent of each other given the class label. This means that the presence of one feature does not affect the probability of another feature occurring, given that the class label is known. Inputs: X the feature matrix, a 2D array where each row represents a sample and each column represents a feature. Y the target vector, a 1D array containing the class labels for each sample in X. Outputs: YPRED the predicted class labels for new data points. Probabilities: the probability of each class label for each new data point. Steps: Training: the algorithm learns the probability distribution of each feature for each class label. In the training data, this involves calculating the prior probabilities of each class and the conditional probabilities of each feature given each class. Prediction: given a new data point, the algorithm calculates the probability of each class label given the feature values of the data point. The class label with the highest probability is predicted as the class label for the new data point. Metrics: Accuracy: the proportion of correctly classified instances. Precision: the proportion of correctly predicted positive instances out of all predicted positive instances. Recall: the proportion of correctly predicted positive instances out of all actual positive instances. F1 score: the harmonic mean of precision and recall. Visualization plots. Confusion matrix visualizes the performance of the classifier by showing the number of correctly and incorrectly classified instances for each class. ROC curve plots the true positive rate against the false positive rate for different thresholds, allowing for the evaluation of the classifier's ability to distinguish between classes. Fine-tune parameters. Alpha: the smoothing parameter for the probability estimates. A higher value of alpha corresponds to stronger smoothing, which can help to prevent overfitting, especially when there are few samples in the training data. Fit prior: a Boolean value that determines whether to learn the prior probabilities of each class from the training data. If set to false, the prior probabilities are assumed to be equal for all classes. Uncertainty methods. Confidence score: the probability of each class label, which represents the classifier's confidence in its prediction. Entropy: a measure of the uncertainty of the prediction, where lower entropy indicates higher confidence. Challenges and fixes. Challenge 1: 0 probabilities. Naive Bayes can encounter 0 probabilities when a feature value is not present in the training data for a particular class. Sample use case that resulted in Challenge 1: a spam detection model trained on a dataset where the word Viagra is only present in spam emails. If a new email contains the word Viagra, the model might assign a 0 probability to it being spam, because it has never seen this word in a non-spam email. Fixes to Challenge 1: Laplace smoothing or add 1 smoothing. This involves adding a small constant value to all probability counts, ensuring that no probability is ever 0. Challenge 2: Feature dependence. Naive Bayes assumes that features are independent of each other, which might not be true in real-world scenarios. Sample use case that resulted in Challenge 2: a credit card fraud detection model trained on data where the feature's transaction amount and transaction location are dependent. A large transaction amount in a foreign country might be more likely to be fraudulent than a small transaction amount in the same country. Fixes to Challenge 2: consider using more advanced methods like tree-based classifiers or support vector machines, which do not make this assumption. sklearn Naive-Bayes Bernoulli NB. Description: Bernoulli NB is a naive Bayes classifier specifically designed for binary features 0 or 1. It assumes that each feature is independent of the others and calculates the probability of a given class based on the probability of each feature being present or absent in that class. It's particularly useful for text classification, where features represent the presence or absence of words in a document. Inputs: X a 2D array of binary features 0 or 1 representing the input data. Each row represents a data point, and each column represents a feature. Y a 1D array representing the target labels for each data point in X. Outputs: Self the trained Bernoulli NB model instance. PredictProbX returns an array of probabilities for each class, given the input features in X. PredictX returns an array of predicted class labels for each data point in X. Steps: Training. The model calculates the prior probabilities for each class based on the frequency of each class in the training data. For each feature, it calculates the probability of that feature being present 1 and absent 0 in each class. Prediction. For a new data point, the model calculates the probability of each class based on the features present in that data point. It then assigns the data point to the class with the highest probability. Metrics. Accuracy: the proportion of correctly classified data points. Precision: the proportion of correctly classified positive samples among all predicted positives. Recall: the proportion of correctly classified positive samples among all actual positives. F1 score: the harmonic mean of precision and recall. Visualization plots. Confusion matrix: a visual representation of the model's performance, showing the counts of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve plots precision against recall for different classification thresholds. Fine-tune parameters. Alpha: a smoothing parameter that adds a small value to the feature probabilities to prevent zero probabilities. Binarize: a threshold for converting features to binary values. Values above the threshold are set to 1, and values below are set to 0. Fit prior: whether to learn class priors from the data or to use uniform priors. Uncertainty methods. Confidence score: the probability of a data point belonging to its predicted class, calculated by the PredictProba method. Entropy: a measure of the uncertainty or randomness in the model's predictions, calculated as the negative sum of the probabilities of each class multiplied by their logarithms. Challenges and fixes. Challenge 1: Data sparsity. Bernoulli NB can struggle with sparse datasets, where many features have a value of 0. This can lead to overfitting and poor generalization. Sample use case that resulted in Challenge 1: text classification with a large vocabulary, where many words are absent in most documents. Fixes to Challenge 1. Increase the smoothing parameter alpha to reduce the impact of 0 probabilities. Use feature selection techniques to remove irrelevant features and reduce data sparsity. Consider alternative naive Bayes models like multinomial NB, which are better suited for handling sparse data. Challenge 2: Class imbalance. Bernoulli NB can be sensitive to class imbalance, where one class has significantly more samples than the others. This can lead to the model favoring the majority class. Sample use case that resulted in Challenge 2: fraud detection, where fraudulent transactions are much rarer than legitimate ones. Fixes to Challenge 2. Oversample the minority class or undersample the majority class to balance the dataset. Use class weights in the model fitting process to give more weight to the minority class. Consider using a cost-sensitive learning approach that penalizes misclassifications of a minority class more heavily. sklearn, Bayesaivebayes, categorical NB. Description: Categorical NB is a naive Bayes classifier designed specifically for categorical features. It operates based on the principle of Bayes' theorem, assuming that features are conditionally independent given the class label. Inputs: X, a 2D array of shape n samples. N features representing the training data, where each row corresponds to a sample and each column represents a categorical feature. Y, a 1D array of shape n samples, representing the target class labels for the training data. Outputs: self, the fitted categorical NB estimator. Predict probx returns the probability of each class for the input data X, represented as a 2D array of shape n samples. N classes. PredictX returns the predicted class labels for the input data X, represented as a 1D array of shape n samples. Steps: training phase. Calculate the prior probabilities of each class based on the training data. Calculate the conditional probability of each feature value given each class, using the frequency of each feature value within each class. Prediction phase. For each new sample, calculate the posterior probability of each class using Bayes' theorem, taking into account the prior probabilities and the conditional probabilities of the features in the sample. Assign the class label with the highest posterior probability to the sample. Metrics. Accuracy represents the proportion of correctly classified samples. Precision measures the proportion of correctly predicted positive samples among all predicted positive samples. Recall measures the proportion of correctly predicted positive samples among all actual positive samples. F1 score the harmonic mean of precision and recall. Visualization plots. Confusion matrix visualizes the distribution of predicted and actual class labels, revealing the types of errors made by the model. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, providing insights into the model's performance in distinguishing between classes. Fine-tune parameters. Alpha, a smoothing parameter that helps prevent overfitting by adding a small value to the counts of each feature value. A larger alpha value implies stronger smoothing. Uncertainty methods. Confidence scores. Categorical NB can provide confidence scores for its predictions, indicating the probability of the predicted class being correct. Challenges and fixes. Challenge 1: data sparsity. If the training data contains infrequent feature values, the model might overfit and make inaccurate predictions on unseen data. Sample use case: a dataset with a large number of categories for each feature, but only a few examples for each combination of categories. Fixes: increase the size of the training data to improve the statistical significance of the feature. Value counts. Apply feature engineering techniques like combining infrequent categories or using a smoothing parameter alpha to reduce the impact of sparse data. Challenge 2: feature independence assumption. The assumption of feature independence may not hold in real-world datasets, leading to biased predictions. Sample use case: a dataset where features are correlated. For example, features describing different aspects of the same entity. Fixes: explore using more sophisticated algorithms like Bayesian networks or decision trees that can handle feature dependencies. Perform feature selection to remove redundant or correlated features before training a categorical NB model. sklearn, naive Bayes, complement NB. Description. Complement naive Bayes CNB is a variant of naive Bayes that performs well with imbalanced datasets. It uses the complement of the features present in a given sample to predict the class probability. Instead of directly calculating the likelihood of each feature belonging to a class, CNB calculates the likelihood of the feature being absent in that class. This approach helps to mitigate the bias introduced by imbalanced classes. Inputs. X. This is the feature matrix. A 2D array of shape n samples. N features where each row represents a data point and each column represents a feature. The features should be categorical or numerical. Y. This is the target vector. A 1D array of shape n samples, containing the class labels for each data point. Outputs. Self. The fitted complement NB object. Predict probx. This method returns the predicted class probabilities for each data point in X. The output is a 2D array of shape n samples. N classes where each row represents a data point and each column represents the probability of belonging to that class. Steps. Calculate the prior probabilities for each class based on the training data. For each feature, calculate the probability of the feature being absent in each class. Use these probabilities to calculate the complement probability of a data point belonging to each class. Predict the class with the highest complement probability. Metrics. Accuracy. This metric measures the percentage of correctly classified instances. Precision. This metric measures the proportion of correctly predicted positive instances among all predicted positive instances. Recall. This metric measures the proportion of correctly predicted positive instances among all actual positive instances. F1 score. This metric is the harmonic mean of precision and recall. ROC AUC. This metric measures the area under the receiver operating characteristic ROC curve, which represents the trade-off between true positive rate and false positive rate. Visualization plots. Confusion matrix. This plot visually represents the number of correctly and incorrectly classified instances for each class. ROC curve. This plot shows the trade-off between the true positive rate and false positive rate at different classification thresholds. Fine-tune parameters. Alpha. This parameter controls the smoothing of the feature probabilities. A higher value of alpha leads to stronger smoothing. Fit prior. This parameter determines whether to calculate the prior probabilities from the training data or assume them to be uniform. Class prior. This parameter allows you to specify the prior probabilities for each class. Uncertainty methods. Confidence score. The probability assigned by the model to the predicted class represents the confidence score. Challenges and fixes. Challenge 1. Feature sparsity. When dealing with very sparse datasets, complement NB might struggle to learn accurate probability distributions. Sample use case. A dataset with a high percentage of missing values or features with low frequency could result in sparsity. Fixes. Consider using a feature selection technique to remove irrelevant features or employ data imputation methods to handle missing values. Challenge 2. Imbalanced datasets. While complement NB is designed for imbalanced datasets, it might still struggle in cases of extreme class imbalance. Sample use case. A dataset where one class significantly outnumbers the other classes might lead to biased predictions. Fixes. Use oversampling or undersampling techniques to balance the class distribution or experiment with other algorithms specifically designed for imbalanced datasets, like SMOT or balanced bagging classifier. sklearn, naive Bayes, Gaussian NB. Description. Gaussian naive Bayes is a probabilistic classifier that assumes features are independently normally Distributed. It's a simple yet effective model for classification tasks, particularly when dealing with continuous features. Inputs. X, a 2D array of shape n samples. N features representing the training data, where each row corresponds to a sample and each column represents a feature. Y, a 1D array of shape n samples, representing the target labels for each sample. Outputs. Self, the fitted Gaussian naive Bayes model. You can use this model to predict the class labels for new data. Predict probux. This method returns a 2D array of shape n samples. N classes, where each row represents a sample and each column represents the probability of that sample belonging to each class. Steps. Training. The model learns the mean and standard deviation of each feature for each class from K. Training data. This forms a probability distribution for each feature per class. Prediction for a new sample. The model calculates the probability of that sample belonging to each class based on the learned distributions of features. The class with the highest probability is chosen as the prediction. Metrics. Accuracy. The proportion of correctly predicted samples. Precision. The proportion of correctly predicted positive samples out of all samples predicted as positive. Recall. The proportion of correctly predicted positive samples out of all actual positive samples. F1 score. The harmonic mean of precision and recall, providing a balance between them. Visualization plots. Decision boundaries. You can visualize the decision boundaries of the classifier, showing how it separates different classes. Feature importance. You can plot the mean and standard deviation of each feature for each class to understand their importance in the classification. Fine-tune parameters. Priors. An array of shape n classes, specifying the prior probabilities of each class. If not specified, they are estimated from the training data. Smoothing. A float representing the smoothing parameter for the variance of each feature. This prevents overfitting by adding a small value to the variances. Uncertainty methods. Probability estimates. The model provides probability estimates for each class, giving an indication of its confidence in the prediction. Confidence intervals. You can calculate confidence intervals around the probability estimates to understand the range of possible outcomes. Challenges and fixes. Challenge 1. Feature dependence. The Gaussian naive Bayes model assumes feature independence, which may not hold true in real-world data. This can lead to inaccurate predictions if features are strongly correlated. Sample use case. A dataset with features like height and weight that are highly correlated. Fixes. Feature engineering. Transform features to reduce dependence, such as using principal component analysis (PCA). Alternative models. Consider using more sophisticated models that handle feature dependence better, like random forests or support vector machines. Challenge 2. Outliers. Outliers can significantly impact the mean and variance calculations, leading to inaccurate predictions. Sample use case. A dataset with a few extreme values in a feature, such as age, having a few individuals with very high ages. Fixes. Data preprocessing. Remove or impute outliers before training the model. Robust estimators. Use robust estimators for mean and variance calculation that are less sensitive to outliers. sklearn, naive Bayes, multinomial NB. Description. Multinomial naive Bayes is a probabilistic classification algorithm that is commonly used for text classification tasks. It is based on the Bayes theorem and assumes that the features are independent of each other given the class. Inputs. X. This is a 2D array representing the input features. Each row represents a data point, and each column represents a feature. Y. This is a 1D array representing the target labels for the data points in X. The length of y should match the number of rows in X. Outputs. Self. This is the fitted multinomial NB object. It can be used to make predictions on new data points. Steps. Training. The algorithm first calculates the prior probabilities of each class. Then, for each feature, it calculates the conditional probability of that feature given each class. These probabilities are stored in the fitted multinomial NB object. Prediction. Given a new data point, the algorithm calculates the posterior probability of each class given the features of the data point. The class with the highest posterior probability is predicted as the most likely class. Metrics. Accuracy. The proportion of correctly classified data points. Precision. The proportion of correctly classified positive data points among all data points predicted as positive. Recall. The proportion of correctly classified positive data points among all actual positive data points. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. This plot shows the number of true positive, true negative, false positive, and false negative predictions. ROC curve. This plot shows the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters. Alpha. This parameter controls the smoothing of the probability estimates. A higher value of alpha corresponds to more smoothing, which can help to avoid overfitting. Fit prior. This parameter controls whether to learn the prior probabilities of the classes from the data or to use a uniform prior. Uncertainty methods. Confidence scores. These are the posterior probabilities of each class. They can be used to estimate the uncertainty of the predictions. Challenges and fixes. Challenge 1. Data sparsity. When dealing with text data, it is common for some words to appear very infrequently, which can lead to zero probabilities for those words. This can cause problems for the multinomial NB algorithm. Sample use case that resulted in challenge 1 when using multinomial NB on a dataset of customer reviews. If a particular word appears only in a small number of reviews, it might have a zero probability in some classes, leading to inaccurate predictions. Fixes to challenge 1. The alpha parameter can be used to address this problem by smoothing the probability estimates. Challenge 2. Zero probabilities for unseen words in the test data. This can happen if the test data contains words that were not seen in the training data. Sample use case that resulted in challenge 2. If a new product review contains a word that is not present in the training dataset, the multinomial NB model will assign a probability of 0 to that word, leading to inaccurate predictions. Fixes to challenge 2. The alpha parameter can be used to address this problem. By setting alpha to a small positive value, the algorithm will assign a non-zero probability to unseen words.